sharing my screen. Okay. Let me know if you are able to see this screen.
Yeah,
Yes.
presentation is visible.
Okay, nice. So let's summarize from our last class, last Monday. So what we finally see is that so basically we were trying to find the best fit line. Now we all come to the agreement that okay, for different values of theta 0, theta 1, there could be many infinite set of theta 0, theta 1. Each theta 0, theta 1 will have some cost function. In our case, it was the mean squared error. So ideally what we decided that best theta 0, theta 1 would be the one which we get the model tried to get the least value of or the approx towards the least value of cost function. Therefore, what it does is try. So, for example, it starts from here. We keep varying the values of theta 0, theta 1. It starts moving into some directions. This is one set that after doing changing the value of theta 0, theta 1, it reaches this local minima, this minima. So that's a good answer. That's a good set of theta 0, theta 1. Or there so now there could be the cases that we somewhere started here or we started here and we start moving and we end up in some other local minima. So that's a one set of theta 0, theta 1. So this is how now we can start finding the best fit. Now question arises that what is the right way that we should pick theta 0, theta 1. So if we just write a for loop, so that gonna take a lot of time on two variable. However, if we have 100 variable, then the computation would be 100 times, not 100 times, exponentially 100 times more. So we will not even able to achieve the problem in this lifetime. So what is the right way? Therefore, we discussed that the algorithm which we're gonna see is that is known as gradient descent algorithm. As name suffice, gradient we generally says to these concept where gradient basically kind of a slope. We want to ascend some slope in the direction towards the minima. That's how a gradient as descent terms is there. So let's formalize our question now. Let's frame our question, and this is how we frame in almost all the machine learning algorithms. We want to decide some optimal cost function. We already decided that okay, this is gonna be a squared mean error. And what was that? If you remember, this was m was the number of data points. It was yi minus phi. This is I equals to 1 to m. This is number of rows. Yi minus yi hat. This is how I used to when I used to write y hat. This is represented as y hat. So when you see this term, so this means this is the predictions. This is how the predictions are denoted in terminologies. So y hat, this is our cost function. So we start pseudo steps gonna be initially we start with some random theta 0, theta 1. We pick any random theta 0, theta 1. The goal would be to update theta 0, theta 1, such as we want to reduce this cost function value. This is our goal. Now we're gonna keep repeating this step we're gonna keep repeating until we reach the minimum value of cost function or close to that. So we keep on making some changes. Let's note this changes as delta, some delta changes. We always keep changing theta 0, theta 1, delta changes, and we keep calculating j value, and the j value should decrease, and and let's reach to the point when it reaches or to the approximate minimum value of j value. The theta 0, theta 1 corresponding to this term would be our answers. Now, how we decide that we have reached the minimum value or close to the minimum value of j, that we're gonna see. However, just to remember, this term is known as convergence. So in terminology, we see that we keep on changing the value of theta 0, theta 1 until our model algorithm gets converged or we get the convergence. Right now, as I mentioned, just randomly updating it, so that's a huge time effort. So is there any some good way to do this stuff that we're gonna see, and therefore we're gonna understand.
Raj,
Hmm.
just one question. Just wanted to clarify. We are still discussing about finding the local minima, right?
not local minima. So this is discussed. Now our goal is to find the best local minima. That's the right term. See, as I mentioned here, we started something, we reached here,
Yeah, yeah,
right?
yeah,
We started here, we reached here, maybe
yeah,
here,
yeah.
right? So as of now, our goal, yes, we would try first goal. Let's go to the minima, local minima, right?
Uh-huh.
Right.
Yeah.
Then we gonna see, can we do something better than that, right? So
Yes,
that we're gonna see.
obviously.
So
Yeah, yeah.
that would be some modifications on top of gradient descent,
Okay,
right? We're gonna discuss that. But
okay,
let's reach some local minima because that local minima would also be a good answer
okay,
to the problem, right? Okay. So good question. We are trying to reach at least one local minima. That's our goal. So let's start with problem explanation board here. So as I mentioned here, we chose some theta 1, theta 0, just to understand. We start decreasing that. We start making some changes to theta 1. Let's start writing this thing. Initialize parameters theta 0, theta 1. So by default, let's we initialize some value, val 1, theta 1, val 2. This is initialized. We gonna see what are the best techniques of initializing all the parameters. Now what we decide, we gonna decide some learning rate. I'm gonna discuss this thing. So they are gonna be first parameter which is unknown to you. That's the learning rate, right? 1 minute. That's the learning rate. Now, what we're gonna do? This is a step three. Suppose now j function is like j theta 0 theta 1. What I'm gonna do? I'm gonna calculate the gradients. Now here we are just two parameters. So you remember we discussed the term partial derivatives. So what we will do, we will take the very first partial derivative of cost function with respect to theta 0. So what happened when you do such partial derivatives, then theta 1 becomes the constant. So that's the property of partial derivative, or one of my homework from last session when I asked partial derivative or derivative, what's the difference? In partial derivative, when you do derivative with respect to some variable, the other one becomes constant. So, and when you do with respect to theta 1, then theta 0 becomes constant, right? This is the only thing which you need to remember. So if in your case there are n number of features, theta 0, their corresponding coefficients are theta 1, theta 3, and so on. So when we are going to do derivative of j cost function with respect to theta 2, then every other terms becomes constant. That is it. So this is how we update parameters, right? Initially, some random initialization, some alpha rate. I'll explain you this thing. We do this thing, and we do theta 0 minus alpha, derivative of j cost function with respect to theta 0, and after subtracting, this becomes the updated theta. This is a updated theta 0. We will keep repeating this term until we reach the convergence as mentioned. Now before jumping to the next slide, let's try to understand what exactly is happening here, right? Let's see that. So what I'll do, I'll mention this thing here. I mentioned this thing. Let me clean it. Just a moment. Right. See, we are here. Just see, this is theta 1. Just to understand, this is j. We have seen multiple example. Initially, for some theta 1 value, which are very far, our cost would be very high. Now we will do some slight delta change here. That delta changes this thing. When we make some reduce the theta 1 value, this will reduce the cost function value will start reducing. Optimal value will reach somewhat here. When we start moving away from theta 1, we start moving, the cost value will start increasing as we move away from the appropriate theta 1 value. Now what we see here is that minus, if you calculate the slope here, partial derivatives are nothing. The derivatives are nothing but the tangents or slopes. So if you calculate the slope at this point, it is in this direction. If you calculate the slope here, it is in this direction. So this negative direction says that always subtract some delta opposite to the direction of the slope. So this is nothing, it's just that the minus terminology is doing what? As you move towards theta 1 in this direction, do subtract. right? Here in this direction, this is a tangent log. If I am away here, this is my updated value. I am very far. What do you want? You want to subtract something from here. So this is a minus thing, right? This is a negative part because slope is here. Negative of that will make my theta move here. If I am somewhat somewhere here, I want to, move it this direction. That's what is minus is taking care of. The whole goal of minus is to move theta in this direction toward here, theta in this direction toward here. That's what negative is doing. What partial derivative? This is slope. This is slope. And I already mentioned in the next previous session that when you take the partial derivatives, you always try to make the slope equal to 0, which assumes that the tangents always, if 0, that's denotes the local minima. That's what is happening here. Alpha, the relevance of alpha, let's see here. So suppose you are somewhat here. You are somewhat here. My alpha is very, very small, say 0.0000001, say 10 raised to the power minus 6 is my alpha. So what happened? The, 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 the theta will update very slowly, right? And it may take hundreds of hours to reach here. So that's huge computation timing. So, so very low value of alpha means we are moving very slowly towards our goal. Now what happens if we make very high value of alpha? So what happens? The speed become faster. Speed become fast, but what happen while moving? It will jump like this way. It might happen that when you are here, the next value of alpha or the next movement might make you pass this local minima. You jump somewhat here, right? So what happen exactly? Keeping a very high value of alpha, you will keep jumping like that, right? From here. So the local minima will always bypass because you are jumping very high, very high steps. So you will not able to reach, the local minima. So that's a drawback. Low value means you takes very long time, 100 hours. So practically not good for the model training. High value of alpha, you jump very fast. So there is a chances that you miss the local minima. If you are here, you might jump to here. So what we want a optimal value of alpha, optimal value of alpha. This is what we want, and that's the goal of this thing. That's the goal of this alpha. That appropriately adjust this alpha such that the training takes a decent amount of time. So that's a trade-off. In general, you will see in the practice, the optimal value of alpha is that we start with somewhat 10 to the power minus 3. Then after few iterations, we all change it to 10 to the power 1, 10 to the power minus 1, then 1, 0, and 1. Maybe that's it. That is it. So that we're gonna see how we do that. But for just to understand this whole term, we move slowly, not slowly, with a decent pace. We reduce the derivative, and this is how we update all the theta 0, theta 1. So if we keep doing that, we will update all the thetas. In the next the theta 0, theta 1 will be updated. We move somewhat from here to here. The next iteration, repeat the same process. We move here to here. We keep on repeating until we reach here. So this is how your gradient descent algorithm works. You descend some cost function towards the direction of local minima by updating the values of updating by update by the rule which updates parameter in this manner, valid for all the theta n, right? And we keep doing this thing until we reach the convergence, means we reach the somewhat here, right? So guys, any doubt in this thing
Yes.
that
Uh,
j-
First of
yeah.
all, I'm just assuming that we are
Hmm.
just looking at simplest curve for time being, and maybe we'll jump to the different shape afterwards.
Okay.
As
Hmm.
we get this up and down many times, so we'll maybe. So I'm just assuming that we are looking at the simple curve. Okay. Now
Yeah.
my question is here at step number 2, we are choosing the alpha, right? But if our alpha is wrong, when do we come back to step 2, or how do we decide if my alpha is wrong or not?
Okay. So let's discuss this alpha thing. So first thing, uh you mean to say if my alpha is wrong, right?
Yeah, so what I understood is if alpha is too small, it will take too much computation,
Right. Hmm.
but we'll find the exact lowest point, minima exact, we
Right.
can
Hmm.
find if the alpha is too high. But we can't keep alpha too high practically because it takes too much computation. So
No,
we
no,
just,
reverse of that. If we takes alpha is small, that's too much
yeah,
of
yeah.
computation. If alpha is large, we might miss local minima, right? Yeah.
Yeah, sorry.
Okay.
Yes, yes, yes. And so that's why, to avoid too much computation, we take alpha as large as possible, and then, but then how do we decide, or how do we know
Yeah.
that if we
Right.
have missed or not
Right.
the lowest minima? So
So good
I'm,
question. Yeah. I got your point. So
yeah.
let's comment on alpha, how to take the alpha. But with that, I also will answer the thing how we reach the convergence. So we will solve both the questions, both the answers with this question, right? So alpha is wrong. So again, we might jump from here, or we takes a lot of time. And how we decide that stop the training, we have already reached somewhat in this area. So that's the convergence. So let's answer both thing here. So first thing, not the answer, just a practical approach. Uh, with the research being done in this area, we not always, we always try with the alpha somewhat here, this thing, right? But how this is achieved, I'll tell you later. Minus 0, which is always 1, and then 1. Now, let's answer this thing. So what happened in this step, when we calculate loss function, what happened? You will calculate the cost function. Let's say iteration. Let's name it. Normally it takes lakhs of iteration to complete the training, but just to answer iteration 1, let's name it I1, iteration 2, iteration 3. Why iteration means this repeat process. Iteration 4, iteration 5. At this point, my cost value was say 100, right? This value was 100. Iteration 2, my cost value was 99.9, 99.98, 99.97. First thing, initially I will keep on running the iterations, hundreds or thousands of iterations. It runs very fast if we are just working structural data. Now here you're gonna see some of the caveats. For example, my j started, my j started, start decreasing, but I am I am also plotting the graph here with respect to iterations. What I'm seeing, instead of fluently going down, I'm seeing my j's are moving. Initially it will not always go like that, it will always go this way, but overall it will go towards down. But what I'm seeing, after iteration 100, iteration 200, 300, my j's has not my j's are not going towards the local low direction. So here this is the idea that this thing is not converging, is not going toward convergence. So you have to always keep plotting towards the training. So what happened when training happens, we also keep tensor boards ready. Tensor board, or this, let's use the normal term, some live chart ready, where we are also seeing the plots of the training iterations and cost. Overall goal is that cost has to decrease. So of course, iteration 1, iteration 2, cost might happen that this is 99.8, this might be 99.9, but again 99.7, that's okay. But over a good margin difference, iteration 1, after 100 iteration, it should decrease. It should decrease. But what I'm seeing, this is iteration 1, this is iteration 100, but after iteration 200, the cost is somewhat here. After iteration 250, the cost is somewhat here. So I am not seeing a proper divergent convergence towards the lower side. So there are two probabilities. Either we hit some local minima here, some local minima, some bad minima, and we moved up, or that's the one thing, or that would be the practical local minima in that area. So you always keep plotting your iterations versus cost function. You have to make sure, and again you have to always make sure that my j values should decrease downwards toward the iteration also. There is a term alpha. When I choose alpha tends to power minus 3, I always also plot the values of alpha and the j values. So in general, I need to see what is the flow of cost function with respect to alpha. So there are a concept known as hyperparameter tuning that I will not go much here in detail, but just to understand this, in hyperparameter tuning, what we do the same iterations. Suppose we iterate for 1,000 times, we do the same thing with alpha equals to 10 raised to power minus 3, same thing with alpha equals to 10 raised to power minus 2, right? We do with all the alphas, and when we evaluate on the test set, and then we finally choose the alpha which gives us the best result, that becomes the best alpha chosen. And this part is known as hyperparameter tuning. When you are tuning your parameters to get the best result, that's the second approach. It's not always fixed that I start with just 10 raised to the power minus 3 and my training is over. I will change alpha accordingly to the need. Now you will say how according to the need. So what happened initially when, and you will understand, try to understand practically, we are very far away from J. Now at this point I am okay, I am okay to move little faster. I'm okay to move faster. But after few iterations, say 1,000 iterations, if my cost functions are keep on decreasing appropriately, I might assume, or practically that should be the case, that we have reached closer to the local minima. Then my goal would be to reduce the alpha. So this happens. This is a practical second approach. You start with some lower value of alpha this way, right? And then keep changing it according to the need. So that's the second approach. So alpha is not always fixed. You have to vary alpha. You have to vary alpha. You have to also plot the cost functions value. If I am seeing after 100, 200, 300, 300, I am not converging. So there are two things happens. My alpha might not be right. That needs to be checked. Need to be checked. Needs to be checked. That's the one thing. So yeah. Now did it make you understand now, or any
Yes,
questions in
somewhat.
this?
So, yes, so somewhat. So, maybe I can repeat and you
Yeah.
can confirm.
Hmm.
So, the step, what we are doing is we are choosing first alpha, let's say 10 raised to minus 3, and then we are trying to find the curve of gradient so that we can find the local minima, right? And then we look at it, and so for example, as you plotted here, if it is going up, then we can maybe spot or say that okay, this might be the area where we can find, or these are the 2 3 areas where we can find the local minima, and then we maybe choose another alpha, and then we plot it again, we compare, and then we change the alpha, we plot again, and then finally we come to know that okay, this is my local minima. Is that right?
Yeah, that's right. And final answer, how you decided the same thing. You have reached some local minima. You have reached the convergence. So what happened in general? Again, it will come later. Normally, when we train model, suppose we have the data which we got is 90,000 of data input. These are rows. Maybe some same housing problem which we discussed already. This is a row. So what we do in general, not fixed, now I'm saying, we divide this 90,000 or whatever the data we have. 90,000 may be small, not much, it depends on the condition. We divide it into two sets: train sets and test set, also known as evaluation set, in 75 to 25 ratio. So just to make math easy, this is say 1 lakh. So training becomes 75,000 rows. 25,000 becomes our testing set. Why I have kept this 25,000 as a test set? Because after training this model on 75,000, I want to check how good it performs on the test set. So test set, we already have the ground truth actual values. We find the predicted values I had and we compare. Then we see, okay, if my model makes sense, right? So I can train model 1 with alpha equals to 10 raised to the power minus 3 maybe. So, and then I can say on test set how did it perform. But this is all about convergence. But anyway, come to this point, how to reach the convergence here. So what happened? I will start two things, two diagrams, or what I say chart, live chart on TensorBoard or some UI. So you see in machine learning, uh, there are a lot of data is produced during the that. So either you can log data in some std out or in some file, but that's redundant to check every time. So what we always do during the training, we also show the artifact. When I say artifact, it means the errors, the alpha values, etc., all the parameters on UI on some dashboard, so that we can also visualize this thing lately, and we can discuss that okay, this was the graph. So if I have my graph ready somewhere, now I could see okay, this point the loss was reduced. So see what happened. So there are let me remove this thing just a moment. Now this not all answers would all questions would be answered with this thing. I am plotting. This is my 75,000 of rows. This I'm talking about train. This is test data 25k, right? Mm. This is J, same cost function. This is J, right? And this is iterations. Thousand. I start with 100. So it starts with 0, 1, 100, 200, 300, 400. Let's maybe going to 1,000 iterations. It goes long, but it takes some time. 3 lakh of iterations, 4 lakh of iterations. It happens within hour, within sometime within minutes for structural data, but for image data it takes 3 days, 2 days, 3 days. But since this is structural data, our computation, our RAM, we have very good what I say, the good capacity of RAM, so things become faster. Now what happened? It 100 iterations. You know the model is not trained, so the J value will be very high. And what happens on the trained data? As we move ahead, this value will start decreasing. A one point will come where the cost will become plateaued. It not always straight, but it becomes plateaued. So this is the plateau point. The same point, the same iterations, 200, thousands. At 100 points, model object would be M1. So these are checkpoints. So by 100 iterations, our model has trained a little bit. 100 iterations, the theta is updated 100 times. So let's check. So what happened? We also evaluate our M1 on 25,000 points. We say, okay, this is the cost. So parallelly, what would be happening here? This will come, this will start going down, and then one point it will start going up. No, when you see the plot, you will see the point at which the train, the model evaluation cost value here become plateaued, but on test it start increasing. That's the point. That's the point. Corresponding to that becomes your appropriate stopping point, model checkpoint. So you will pick this model object. That our model object is nothing but the best set of theta 0, theta 1, and so on. And you will use this model object in your machine, in your application. So did you guys understand this thing? You know, so we are parallelly showing two boards here. This is a general characteristics of what happen when you train a model. On train, it is supposed to go down. At one point when it starts plateauing, it will not go up because you are uh, you are training on train data and also evaluating on the same, right? But in test, what will happen? The cost function value will start increasing. So so that's the point where we choose this thing. Now that's one example. Can anyone suggest, is there any other metrics which I can use on Y to decide whether my model is trained or not? So first question, does it make sense what we are seeing here and here on train data and test data? How to decide that we have reached the convergence,
Yeah, it makes sense. Yeah.
right? No, because train it will plateaued mostly
So
or
right
on.
side, you're like parallelly, you're checking the like whatever the this maybe theta 0, theta 1 parallelly, you're trying to implement in the right side in training model, and you're looking for the cost on training
Yeah,
data.
yeah. So whenever my iteration counts these multiple of 100, so I might write a function. I is the iteration when I mod 100 equals to 0. At this point, uh, create append this graph for both. So what happened? Finally, when the training converges or we reach, we can plot this thing and we can see this thing. So test. This is the point where we are supposed to stop. Now, second question. Again, this is a practical aspect. Theoretically, this is what it is. But now you might ask that, okay, how I model is training. So how I make model understand that you should stop rather me always checking the dashboard. So there are multiple techniques you will see later. There are techniques known as early stopping. Again, this is not some rocket science. This is already the methods created by the libraries. machine learning library. Early stopping says that uh, if I say early stopping 100, so what it will does, it will check, okay, my cost function is 100. What it will do, it will say in the next 10 iterations, if the algorithm is not seeing a decent change in loss, the loss is not loss plateauing somewhere, so it will stop. This will says, okay, now the j is not decreasing appropriately, so we should stop. So early stopping means stop by yourself, just check for next 10 iterations. Even if there is not a sustainable or a decent change in the j, stop. So model will stop. That's one technique, early stopping. It it also checks the moment it sees the j, or there are already like functions written, it sees the j value is increasing for next 10 iterations, stop. So it will stop. So these are the ways of making them stop by itself, but practically, theoretically, fundamentally, this is what it is, right? This is how we always look for this thing, error. The error in train, this is the best fundamental, the safest and the pure fundamental way of figuring out when to stop training. It will start decreasing, test it will also start decreasing, one point will come, this will start plateauing, and this will start moving up. So it, and then we figure out, okay, what is the which iteration it happened, and then we take the model checkpoint. So machine learning also does, after every iterations there's a provision, we checkpoint it. So the model is generally created, suppose model name is am, it would be checkpointed like this way. CKPT is nothing, it's the extension 100.ckpt. And suppose at 500 checkpoint, that's the one where this thing starts going up, then this becomes our answer, this becomes our model input. We will use this model
Uh,
object for our further use, and we stop the training.
just just one question. So on left side we are having this test, sorry, training data, left side training data.
Huh.
So here when I increase my theta value, okay, on I'm going towards the right side, okay, still my cost function is plateauing, okay, it's not neither increasing neither decreasing. But why the same time my cost function on test data, why it's increasing? Because it's not supposed to increase now. Because on like my training data, my cost function is not like not increasing or not decreasing. So it
Right.
should behave on other side in a same way. Then why it's
Perfect. Got
happening?
your, so very valid question. Very well. Let's answer this thing. First thing, tell me why it is plateaued. Can you explain this thing? Why eventually what will happen that it will plateaued? So then it will answer your final questions. Generally, it plateaued
So
because the tangents become zero, right? So
yeah,
this
rate
term, this
with
this term,
respect to that.
with respect to this term, it will
Yeah.
always tends towards zero. So when this is zero, theta zero gonna remain as theta zero, right? If this is the case,
Okay.
the j value will come plateaued, right? If
Yeah.
100 is right, that's what. So this terms become so minuscule, so it's close to zero, that becomes negligible, right?
Yeah.
If it is negligible, these become same, so eventually that will plateaued. That's one thing. Now your question is, it should be plateaued here itself, right?
Yeah.
Then why it is going up? Let's answer this thing. Train data and test data. Train data is seen, test data is unseen, right?
Yeah.
If I am training on some model, if I'm training a model on the data which is already seen by me, then model will start memorizing it rather than learning the patterns. Our whole goal is to learn the patterns, not memorize it. So that's why it is a saying that you never evaluate on the data which is already seen by the model. So trained data is already we are passing into the model building. So
Yeah.
for those data, the model knows what is the y actual, right?
Mm-hmm.
So
Mm.
that's the biasness which is always there. So we never evaluate on this data. But here, see, this is the test data. This will always play two. But on this test data, the cost functions value is gonna be different because there is a different set of unseen data. These data are different, right?
Yes. Yes. Yeah.
Your data is not same. You are working on some different data.
Mm-hmm.
So what theta 0, theta 1 working here, that might not be working here. So
Okay.
that's the
Okay.
point. So and you might also miss here
Okay.
because you might jump from here to here. So that's second aspect. So there are multiple aspects we need to take care of. But if you summarize this thing, only thing which needs to be taken care is that, which is very simple. Keep alpha initially small. Sorry, keep alpha initially. Uh, so there's a range. We start with some, keep alpha in the range of trade-off between low to high, right? That's one thing we need to take care of. How we do that? The term I remember is the hyperparameter tuning, which we will see later, but not related to gradient descent algorithm. And we take the partial derivatives. We keep updating until we reach the convergence. How we reach the convergence, we
Okay.
already discussed. So this is how, this is what machine a gradient descent algorithm is worth.
Yeah.
Now,
And maybe one more thing. Maybe that that one value of theta or theta zero, theta one, maybe working for both the data sets. So that's why maybe we can stop there. Correct now. Means the seen data and unseen data.
yeah. So yeah, this thing. So this term, uh, partially yes, this term will make sure that we have already plateaued. I mean, whatever we could learn from the training, we have already learned. But we also make sure that this will always plateau. So you should not miss this aspect as well. So for example, you say, okay, this is say 10 p.m. in the night in some hypothetical way. You are supposed to see, but you slept. Morning you reach here, you see, okay, this is plateaued. You take this theta, but you forgot to check the test evaluation. But what could have been happen that for this theta it was somewhat here, for this theta we have already reached, you know. So therefore both things has to be matched. It has to be plateaued and it has to be somewhat here, right?
Okay.
So yeah, partially right, but yeah, this is the case. So that's what I want to mention here. Already now you guys explain. If alpha is too small, gradient descent can be slow. It moves very slowly till we reach here. If alpha is too large, gradient descent can overshoot this minimum and it may fail to converge or even diverge. Diverge means when we go up. So it would happen. This is the graph, for example. You started here, you jump here, you jump here, you miss the local minima. You here, just negative sign start playing. The whole negative thing is a very pivotal here. It will, if you start moving alpha, it will shoot you in this direction. Your algorithm will never converge. You will always see the fluctuations of j value going down, going up, going down, going down. Your So this means you are not properly training on theta 0, theta 1, and eventually theta 0, theta 1 will become Ravis. So not meant to be used with the algorithm. So therefore alpha plays a very good role, right? So shall we move further? Uh, so this is in summary is the gradient descent algorithm, a very simple, very one of the finest algorithms in machine learning, and works with charm. I mean, gradient descent algorithm. You will see it used in some other algorithms as well. Descent because we descend, but there are some scenarios where we have to ascend. You will see it later if time permits. There we use gradient ascent, which is just the opposite of the convergence. There we diverge. We try to reach the divergence point. Uh, Gradient descent algorithm. Okay. Now question again. Does it uh, does it suffice that we always reach the global minima? So no. Gradient descent algorithm will help you find the optimal way of theta 0, theta 1 with a local minima. Therefore, if you're working with a gradient descent algorithm, we have to do a lots and lots of experiment with the randomly initialized, not randomly, it is randomly, but there are some techniques behind it, randomly initialized value. So what could happen? You do experiment one, randomly initialize theta 0, theta 1 somewhat here. This might converge you to this thing. Then you do one more experiment, you might start somewhat here, then you converge to this point. Finally, what you will do every time you evaluate on the test data. And finally, after doing all the experiment 1, experiment 2, experiment 3, you will choose the one with the lowest value of j theta. That becomes your becomes a best model, best fitted lines in our case. Now, since this gradient descent algorithm by itself doesn't take care of taking you to the global minima, therefore this is known as vanilla gradient descent, a plain gradient descent algorithm, which does it work perfectly fine, but doesn't guarantee you that you reach the global minima. Therefore, you will see multiple variation on top of that, and we're gonna see it later. Maybe one example I'll cover. So there are ADA grade technique, there are Adam techniques, there are momentum based gradient, there are stochastic gradient based gradient. These all are the variant of gradient descent. Each came after few years by different scientists. Everyone's goal was to, they just worked on one goal: how to find the best set of theta 0, theta 1. So maybe so Adam is the latest and the most useful one. So later, if time permits, we will see how Adam works. Adam is nothing. It's just how the training is happening. They make intermittent changes in the training. Also, they play a lot with the alpha. So basically, they derived some alpha updated. So that alpha will vary after almost every iterations. So alpha is not gonna be fixed. They keep varying alpha based on the training. They see, okay, we are running very fast. They will do some calculations on the back data. They will make the alpha slow. When they see, okay, we are running very slow, they will make the alpha fast. So these are the changes which you will see here in this. So, but again, that's something extra, and we do not need to worry about that. In general, when you will do some machine learning experiment by itself, if some model or some algorithm is using gradient descent algorithm, they by most of the cases they go with Adam and in his Adam technique. Therefore, I will take Adam later. Okay, so let me see what is the time now. Is so 8:16. Let's move ahead. So for others guys, does it at least make 50-60% that what how gradient descent algorithm is working?
Yes, somewhat. I think we
Yeah,
need to look into it a little bit. Maybe we have further
definitely. Yeah,
questions
of
we
course.
can connect
So
afterwards. Yeah.
yeah,
I'm
just
actually
yeah.
struggling a bit, but yeah, I'll have to.
So so at least
What
yeah.
I
So
understood is
mhm, please.
uh, no, no. I mean, what I understood is like I missed in between actually, but in general, it is we are trying to minimize the cost function with the gradient descent algorithm, and the various processes are like you do some like initialization and then reduce the cost function value. So
Mhm,
yeah, it help. Yeah, it's helping me, but I think I'll have to
mhm.
recall or recap once.
So, so yeah, see, so that's of course, I mean that's pretty valid. That uh, so since every class is little technical heavy, and again this the subject, that's how the subject demands it. So I'll
Yes,
prefer
yes, yeah,
everyone to go before coming to the next class, just at least revise the previous class or the summary what we
sure.
did in the last class. So that will definitely help. But again, so far nothing much has left. So in the last three classes we just discussed. The first class is very pretty simple. Last two classes we see linear equation. If everything boils down, I'll write the 5 steps how things works. In our case, linear regression, we wanted to find the best line, and we remember best line means some sets of theta 0, theta 1. Then we decided, you see, we figured out if these are data points, there could be n lines. So what we decided to find some optimal cost function. Cost function is the way through which we decide which is the one we decided to take. These difference, the line for which the sum of these differences are lesser, that is possibly a good line for us. Therefore, we decided, okay, for linear regression, my cost function is the squared mean error. Simple, y high actual value minus predicted value ka square, and take the average of that. That is it. Now we decided to see how we can find the best value of theta 0, theta 1. That's our final goal. Then we understand the concept of derivatives. In derivatives, we decided that this is somewhere we want to reach. This is the j value, this is theta. We want to reach to the theta for which j is lowest. Therefore, decided we move slowly down. And when we decided that if we take the derivative of this cost function here or at any point, if we equate it to 0, then that will give me a value of theta 1, theta 2. Why this thing works practically here? Because tangent or derivatives at
The
local
slope at
minima
that point
always
is
equals to
zero.
0. Right? So we do the derivatives. Now and that becomes we reach today's class. We start with random initialization, we update the value, and we keep doing it that thing until we reach the convergence, which we see here. Right here we reach the convergence. So yeah, please have a look again, and then things will start becoming easier. And when you will see the the machine learning implementation practically, you will see that the theory is okay, it's good to know, but practicality, it's very simple, because everything is doing by the library for us. It's just the dashboards which we need to write by ourselves and see how thing works. So let's finish our 1 hour before we take the break. So I am now going it from just 1 or 2 variable to the practical examples. These are my variables of a housing problem. There could be many. This is my equation. So instead of just 2 variable, we have n variables. This is my hypothesis, also known as y hat. Here uh, I will do the same step. This is what I am doing. This term is nothing but the derivative. After doing the derivative of cost function with respect to some theta n, it just boils down to this thing: y hat minus y square s0 I. This is, we do not need to know, it's just derivative. If we opens the derivative, this becomes thing. That is it. And finally, we will calculate all the thetas, put it here this way, and we calculate the updated j in the second iteration, j in the third iteration. We keep doing this term until we reach the convergence. And this ends our gradient descent algorithm in linear regression. Now, just a moment. So I think we should take a break right now here, because now we're gonna understand some concept that I mean this is what it is. I mean there are many other things which we need to take care of. I just want to before closing, I just want to give you one example. X theta 1, x2 theta 2. Now suppose this is a one number x1 x2 which is in the range of say 10 raised to power 6, say 10,000 q1, some 11,000 q2 maybe. Now there's one more variable which is just in the range of 0.01. Maybe that's the nature of data. 0.01, 0.12, 0.13. Now, would you agree with me? I mean, this number as a whole becomes a huge as compared to just this number. So this means that my y hat is actually getting influenced by this big number. So maybe this could be a very important future, but just because the nature of data is that it is in the decimals, this is in 10 raised to power 4, 3, the overall y hat is totally influenced by this factor. This will affect our predictions. My model becomes biased toward this data, because so so can we, what should we do that so that such kind of steps or things which we need to see it now. So how we can make sure that all the features are not just get influenced by some larger values, right? So we're gonna see feature scaling, we're gonna see mean normalization, how to take care where my data variable is such that, for example, if my one of the data set is balcony, or maybe is post society, so or maybe some section we have value a b c. No machine learning algorithm cannot work on such kind of data sets, categorical data sets, so we call them categories. So this has to be converted into numbers. How we do that, we're gonna see that encoding categorical variable, and then removing multicollinearity, we will see that. So so maybe we take a break for 10 minutes, and then we come back at 8:35. 8:30 would be fine. We come, let's meet at 8:30.
Sure. Yeah.
Yeah.
Sure. Okay.
स्टार्ट करते हैं अब। एक मिनट वेट करते हैं सबका, फिर देन वी स्टार्ट।
We can start, I think. All of us join. Yeah.
ठीक है, स्टार्ट करते हैं। स्टार्ट देन।
Yeah. Okay.
Okay. So now we are moving towards the practical aspect of using the algorithm, using doing linear regression by ourselves. But there are some important points which we need to discuss. So let me do it. Okay. Just a moment. Yeah. Okay. So this is how my data looks like. This is data point. These are variables x0, x1, x2, so on. Yep, we have these many futures. We call it futures, and then we have these many rows. Now, as I mentioned, the thing which I am mentioning, suppose let's discuss with these two variables x2, x3. So the values of x2 are somewhat 15,000, 10,000, 20,000. It could be 30,000, 25,000. It could be say salary, right? Uh, there another feature. It could be say some kind of rating, which raise in the range of say uh, 1 to 3, for example, or 0 to 1. So it could be value say 0 point average rating, 0 0.1, 0 0.9, 1. Overall, these values, how y-hat actually looks. So these values is multiplied by some coefficients q3 dot x3. Now suppose for a time being, I assume my q3 values are smaller. These are generally smaller. So this is 0.01. I keep it same. q3 0.01. So 20,000, 15,000, just to make it easier, 15,000 into 0.01 plus 0.1 into 0.01, this number tends to become 0. So this becomes almost, this becomes 15,000, 1,500. So what do you see? The relevance or the importance of these numbers are so small that it makes a very little change in the overall calculations. It becomes almost close to 0, which at, in compared to this factor, which is very high, very high. This is very less. So overall, this effect is getting turned over or override by the effect of this number. However, if I exclude this x2, this is a very good feature. Uh, this guy rating in this year is 0.9, very good rating, a top performer. So the next, maybe if we are working on some factor which involves this rating, so this factor is totally excluded here, the importance, right? So this thing is known as a problem in specifically seen in all the linear regression problem where the values are not properly scaled. So how you can remove this problem? You can remove this problem by doing the scaling or also sometime normalization. So what happened? Is it possible if I bring all the thing into the same scale? How you can do that? One concept is that if you just take the average, and if you do something like this, x minus x average and x average. So basically you normalize all the equation towards the mean. Or if you do x minus x average max of this whole column, minus mean of this whole column, basically range. So basically what we are trying to do, we are trying to bring this value in the scale of 0 to 1, sometime minus 1 to 1. So if I bring the value here, I scale them or I normalize them, now they have come to the same level, right? Now their effect will not be overridden by other. So these things are known as either feature scaling or mean normalization. Mean normalization is just a technique. How do you normalize? You normalize it by taking the x minus x set, or this could be standard deviation. And you can do it later if you take some example. If you take the mean of these term, which is 300, 500, 600 by 200 minus standard deviation of this thing, denoted by this thing, and this mean you have normalized it towards the mean. Now the values will not be biased. These value will become something 0 0.001, 0 0.2. This will also become 0 0.3, 0 0.2. So they are normalized. This is how you bring all the columns onto the same label, and this is very required when some of the columns are of different ranges. So first we always do the normalization. Now second case, as I mentioned, the x1 is the variable which takes sometimes a value a b. There could be some practical reason behind that why these values are a b c a. So they are the three values. So you cannot, if we write some equation here, then theta 1 into a, this will fail. So there would be error in the code. So you cannot directly use a. So what are the techniques? So if I just say a equals to 1, v equals to 2, c equals to 3, then if I do q1 into 1, then this will unwantedly give the hint to the model that c is better, because or c sub or maybe a is better, because now we have converted into the numerics. That's okay, but being model being just mathematics, it would be now theta 1 into x1. If x1 is 3, is theta 1 dot 3, x1 is 1, is theta 1 dot 1. So it is now mathematically comparing them. So this is not the right techniques. So therefore the technique which we use is known as encoding categorical variables. What we actually do that, we figured out that there are three categories. A would be denoted as, it is 3. So how we do it in our gates, a would be say 1 0 0, b would be 0 1 0, c would be 0 0 1, right? So this becomes our, suppose this is x1, x x1 byte 1, x1 byte 2, x1 byte 3. We name it something. Now this is how you can denote your categories. A B C will expand. Instead of here, the columns will change. It becomes x0 and then x1 underscore 1, x1 underscore 2, x1 underscore 3. So A, this column is removed, it would be written here 1 0 0. This is how you converted them from categories to some encoding. Here we use just plain encoding, and so if it is A, it's just first bit, B is 1, C is 0. Now sometimes also you will see practically, if we know that we are just three classes, then there is no need of taking this third column. If it is 1 0, it is 0 1, it is 0 0, it's automatically understood that this is not the case. This is neither A neither B, this is something else. So there is no need of taking this thing. But anyway, this is just a technique we will see automatically done by the libraries, where you convert strings or characters into number smartly. Not this way, this is mathematical way, but here in the way of encoding them. So this is one step we do. Now there's one more step, which this is known as multicollinearity. Let me explain you. Okay, multicollinearity. Take the example here. If I have a future, I've already discussed this some point of time. This is a size of an house. This is a future. So we have 1800 square feet. In square feet, this is 1500, 2000. Now there are two more data provided by the user. they can provide any type of data, number of houses, number of rooms. So number of rooms, average size of rooms. So if they provide 3, average size they provide is 600. If I write my equation, y hat equals to theta 1 into 1800 plus theta 2 into number of rooms plus theta 3 into 600. So don't you agree that these just two columns, if you multiply, if you take this thing, number of rooms into average size of rooms, this is not the multiplication of them is nothing but this thing itself. So what exactly happening here? You are making a unwanted biasness in the model by considering the effect of this column twice by keeping this thing as well, also by keeping this thing also. This is known as multicollinearity, where exist such columns in the data set who are creating double effect or triple effect on the y value. So this is unwantedly there would be some q4 x4. So this is kind of an unbiasedness which is created here, which is telling the model that see the effect of this variable being taken twice here because you're just summing up. So this is not good for other variables and creating an unwanted biasness toward these variables, which we do not want. That we want all the variables to be unbiased and directly related with the y. So what you can do in case of multicollinearity, either you take this column, either you take this column, or you take these two columns, or remove this column. So this could be a case. I mean, if I remove this column, now take the cases. This is moved. Number of overall size 1800, number of rooms 3. They both are giving the different information. Now the informations are different. But keeping these two figures, or maybe keeping q2 some q dash x2 dot x3. This is exactly giving the same information, so not required. So we need to take care of that. We need to, if there are columns such as x2, x3, x4, if x3 and x2 are highly related with the y, or x4 is highly related to the y, we will remove at least one. We will take just two. So in general, we
So,
do. Mhm.
so Raj, like what you're saying that this variable should be orthogonal to the my y hat, not with so it they should not interact with each other. That's
Right,
what you're saying.
right. So their effect with the y should be with the y itself. Their interaction with the other should not be there. If the interaction with other is there, at least reduce the one. Right? So that thing is pretty much right. So x2, x3, x4, they are pretty much directly related with the y, but also the relation between x2 and x4, the term this term known as correlation, that is very huge. X2 x3 correlation very huge, so I can remove one variable, otherwise they will create the unwanted effect on y. And how we do that? In general, there's a term we have seen in very different languages, correlations. Correlation says that if I increase, you will also increase. If I decrease, you will decrease. So if my correlation is 0.8, 0, anything more, it always led to 0 to 1. 0.5 means it's average correlation, but 0.8, 0.7, highly correlated. Whatever happened with this variable will happen with this variable. If this value is getting high, then there are 900% chances with this correlation that this value will also be high. Now, what practical how we do that? We create correlation matrix among all the variables. X4 here also x1, x4, x2, x3, x4. This will give us some values here. Some will be 0.2, 0.3. Now correlation with themselves is always 1, but now I'm seeing that x2 has very high correlation with x3, 0.9, also high correlation with x4, 0.95. I'm also seeing that x3 has very high correlation with x4, 0.75. In this case, what I can do, I can decide removing any one variable and keep the other two. So this way you will minimize the multicollinearity. So this is also kind of known as EDA, exploratory data analysis. We always need to do before creating a models. So in general, the customers will provide you whatever the data they have. So their data is sometimes redundant or too much data. So you need to intelligently figure out that which data needs to taken. So these are the some steps always in the cycle which I shown in the first class, pre-processing steps, exploratory data analysis steps, which we do while coming up with actual model building. So model building is just 5% of whole task. It's just about doing EDA. Therefore, we're gonna see also in one of the practical session today, if time permits. So these are the 4 steps you need to take care of always. We always scale the data, we always encode variables, and we remove the multicollinearity by creating the correlation matrices. Okay.
Uh,
Yeah.
1 minute, Ranj.
hmm
So here in this feature scaling, or can we go to yeah? So this feature scaling and mean normalization, I guess they're both
I
like one thing only. So
actually
here we are
mhm.
trying to bring like x1, x2 on the same level. Okay. So
Within same
correct,
range.
no?
Yeah.
Yeah.
Within same range,
So
yes.
you're saying that like when like for x1, let's say I am having 10 rows, okay, 10 values. So maybe like when we do this normalize, then all sum of all these 10 rows will be one, correct? Means
Uh,
out of 100 percentage we are making it, na, like that.
yeah, depend so depend on the techniques which you are doing. So mostly there are different techniques which puts your value between 0 to 1 or minus 1 to 1.
Mm,
So it's just so
okay.
the way we are doing that is not always equals to sum. That's not the case because that's just not required. If it is 100
Mm,
200, I do not need to make the after the doing some these steps, the sum has to 1. There's no need of that. It's just that 100 200 will come in one range, 0 to 1 or minus 1 to 1. So that we need to do that here. So just basically
okay,
scaling, just
okay.
plain
Mhm.
scaling in such a way that
But sorry, go ahead.
so basically think practically what I want. If Q2 is in the range of again 10,000, Q3 range, what I do not want to make model understand that 10,000 is greater than 0.1. That's not the goal. My goal is that
Mhm.
10,000 is greater than 20,000. So for on if I convert it onto a scale of 0 to 1, then 1 is greater than 2. So the relevance of 20,000, whatever the relevance of 20,000 with respect to 10,000, that's the same relevance of 1 with respect to 2. So
Yeah,
here,
yeah.
if I bring it onto the same range, the now same range is there. Now these are in onto the same range. Now it's all depend on the coefficients and the
Okay,
interaction.
okay.
Otherwise, one variable will eat the other variable, right?
Okay,
And that
okay,
we do not
okay.
want.
Okay. Maybe with same number, I will divide all row elements
So
in that column.
there are different techniques. If you mean, I should write it one. Mean normalization is one of the techniques, which is nothing but if you do x minus x, and this is mean divided by the standard deviations, then you bring it onto the range of that. This is known as mean normalization technique. You normalize it with the mean. So for example, standard deviation is just one standard deviation. This is one of the techniques, also known as z score. But let's not do it. Overall thing which we need to remember is that we need to bring it into the some scale
Yeah,
which is
got it.
invariant to all the futures, right? That
Yeah,
is it.
thank you.
Encoding also another so just there are min, for example, just to end it, there are min max scalar. What min max scalar does? X minus min upon max minus min. That is also one kind of scaling. So there are different kind of scaling. We see whichever helps us. So if I mean, there's no need of reading scaling differently, but each scaling plays some role here. For example, so there is some robust scaling. For example, if this is my data and some data is here, lying here, so I cannot use mean normalization because just by having this one data point very far away from these data points, my mean is already toward this data set. So if I return something minus mean, that automatically bring a wrong effect here. So I do not want to go with mean normalization here. Then I will go with robust techniques, robust normalization, which is dependent robust scaling, which takes care of doing this whole scaling considering this outliers. They remove the outliers and then do the scaling. So it just depends how you want to scale. But in general, mean
And
normalization works like charm. This thing.
and how
Okay, thank
how
you.
can we be sure that there is no outlier in our actual data, because while training we can know for sure that okay, my one of the data is outside the line, so there is no point of doing the normalization.
right.
But once we train the model with mean normalization, or once we
Mhm.
do it, then when the actual data come, there it might happen that one of the data lies outside.
Perfect. Right. Yeah.
So
Hmm.
so I mean, do we do we train the model with all kind of
No. So
normalization, or the
no, I got a question, right? So the simple steps. In general, we have the data. We do some pre-processing and then do model training. Now, your question, there could be an outlier, there could not be an outlier. So we never left that way. So that's the step. I was about to come that. In
okay,
general,
okay,
if you work with some linear regression, these are the steps which need to take care of, right?
okay,
So let me explain it one by one. Handle missing values. If my data has some, x1, we will not always get the clean data. So there would be some nans or nulls, right? We need to take care of them. Model linear regression never wants null or none, because nan into some coefficients makes whole y equals to null, right? So you cannot deal with nulls. We have to take care of that. So this term is known as handle missing values. Now anyone can tell me one simple technique. This is my data: 300, 150, 200. This for this row I do not get any data. This is null. Again 500, null. Can anyone tell me and how to deal with this null here, or how you think a simple way, how should we go by handling the missing value?
Interpolation.
interpolation.
Interpolation, that's one example. Or or
Averaging.
simplest way,
Can
if nothing there,
can we
take
skip it?
uh, uh, if say this is 10,000 rows, I found nulls in all the columns in just say 100 rows, I can remove that,
Can
right?
Yeah,
Just
skip
straight
it.
away
Yeah.
remove that, skip it. 1% depends on data. 1% in, if my data is lakhs of rows, 5,000 rows, I can remove that. Or remove rows, remove NAs, one thing, fill NA by mean. Take the mean of remaining values and fill that. That's one thing. Now, there is no and if I might fill it with the median, right? It depends my need. Now, then I can, it's all about exploratory data analysis, how I can work upon that. And mostly the data scientists, machine learning engineers work on these problems before applying model. I mean, some of us can use just mean, some of us can have median, some of us can have some custom methods. Now, everybody would be having some different fitted lines. Whose lines would be better? Who mostly deals with the data patterns. Now, what I can say, just for an example, and nothing a part of this course, nothing. I see that there are some X2, for example, which is class A. There C, 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 class C. Now, don't you think I can think some instead of replacing with the mean, why should not I replace this null with the mean of only those values which belongs to class A? Don't, this is, I think, a better way of replacing with the mean, because whatever the nature of C must be different. So this is one of the way. What I can do, mean, take mean of all rows where x2 equals to a. This means say replace all the values, corresponding values where the nulls are, where they are nulls. So I replace. That's one of the better way of fill NA with mean. But yeah, this we can work upon. I mean, this is up to us how we can create some intelligent way of replacing the mean. But the ideal way before going to the any experiment is replace with the mean or median, or maybe remove the rows. So you answered well. Check for the
Um.
outliers. Yeah.
Okay. One question. The last method that you said, maybe when we calculate the mean, we don't consider all the values, just one values from for example x2 so it can be extended for multiple columns as well, right? So for example, x2, x3, x4, x5 column, if certain values are there, then only consider mean of these rows, or
Mean
is
of
it just
mean of
yeah,
column.
Mean of column. Yeah, sorry. But
Yeah, yeah. Mhm.
what we did in the end was we didn't consider all the values in the column. We just considered those values for which x2 had value a, right?
Yeah. So
So
yeah,
can it be extended for further columns as well, or just it is the dependent on only always dependent on only one
no, it is
other
totally
column?
extendable. It's just that
Yeah.
how better we create the relations in the data.
Okay.
So if so, for example, for me, just be with me. If I remember, A is the uh, uh some practical example. A belongs to some A belongs to some very outstanding. For example, B average, C bad. For example, now if we are computing, salaries, they are these salaries are 50K, 60K, 30K, 40K, 10K, 20K. For example, now you will agree that it makes sense if any exists null exists in for A. Why should I take the mean of guys having 10, 20, 30, 40 also? I just replace with the mean of the guys who are already in the A, and that null value are replaced with that thing. So that I wanted to convey here. So it's up to us that what relation we want to. There could be one more column, even better,
Okay.
find granular column on which I can take the better mean or median,
Yeah.
right? So this that is one thing. Uh, how to remove this? Okay. Okay. Now coming to the another point, which is outliers. So outliers are the point which is basically the outliers very far away from the actual data points. If I have some values 100, 200, 150, 112, 100, and then I see some data point, these values are by mistakenly uh, it becomes 10,000. First thing first, can any now you will not be able to plot, or you can plot of course, but it will not be that intelligent that I visualize all the 1 lakh points on data sets and decide, okay, this one is outlier, this one is outlier. That's not a good technique. So can anybody tell me what is the right way of finding the outliers? Okay, so so this I'll explain our terms in. I just take 2 minutes to understand you the normal distribution. You must have heard of this term normal distribution. We have seen in our company when our during the appraisal, our HR or our manager says that we have to fit a bell curve. This is what we have heard. Most of the people would be given this rating, some would be given this rating, some would be given this rating. So this bell curve is nothing but the normal distribution. So what is found in the real world, and most of the data, real data, they are normally distributed. I mean, if you plot them, they always follows this shape. So if this is the salary, it will follow this shape. If this is the height of the people, this will follow this shape. That's the real example. Therefore it is term normal distribution. Second term of this is known as Gaussian distribution, because it was given by Gauss, scientist whose name was Gauss. So what is the the best part of this distribution is that this distribution, this part is lies at the mean, and then there are one standard deviation, two standard deviation, three standard deviation, it could be more. Similarly, minus one standard deviation, minus two standard deviation. Whoever doesn't know standard deviation is a term which says that after reducing a smaller unit, which is equal to one standard deviation, what is the value? So in normal distribution, 66% of the values lies in one standard deviation from -1 to 1. 95% of the values lies in two standard deviation. 99.7% of the values lies in three standard deviation from -3 to 3. Anything which goes beyond that, that are the outer reach, and that we call as the value which are outliers. If I'm very strict, I am working finance domain. This is three standard deviation becomes my outlier. So what I can write, any value three standard deviation, x lower, x higher, plus three standard deviation. any value which are more than equal to x high, or which are lesser than x min, basically lying in this area. These are the outliers. So this way you can calculate, you can figure out, okay, in my column, in my x2, what are the values? So for whatever the values, this condition is true, it means x2 value is greater than x2 greater than equals to x2 plus 3 standard deviation, or lesser than minus 3 standard deviation. That's an outlier. So coming to this point, one technique of finding the outlier is that x plus minus 3 standard deviation. If I'm in financing domain, I do not want to take risk. So what I can do, I'm still okay. Might say that I do not want anything more than twice the standard deviation, 95% values. So that is the case.
This
I am
is X or X bar, this one.
uh, this is sorry. Thanks for correcting me. This is x bar. Because mean plus 3 standard deviation. This is x bar. Right, guys? This is x bar. X bar plus 1 standard deviation in both sides cover 66% of the value. So in general, mathematically, all we will calculate this way, plus minus 3 standard deviation. I was taking the example of 2 standard deviation, means 95% of the values. Suppose I'm working on a finance domain. I'm creating a solution which finds the defaulters, and I just want to be safe. It's even if the conditions, the model says, even makes me of us who are non-defaulters as a defaulter. The system is okay with that, but system doesn't want any defaulter to be, uh, to be saved. So they want to be very strict that even if the customer lies in the last 5%, he is defaulter for the bank. So in this case, instead of 3 standard deviation, I will be strict. Anything more than twice the standard deviation on right, or minus twice standard deviation on left, they are defaulters for me, means outliers. So this way you check outlier. So any doubt in that, in this technique? So this is, this is quite simple, and you will agree that
Yes.
we are just finding the extreme values. So this way you can do in one function, you can just remove the outliers, or at least figure out the
mm,
outlier. Another technique which I want to discuss is the box plot. This you must have seen some graph somewhere here, and this I'm maybe let me remember.
Actually, like maybe I am having one doubt,
Yeah,
may not
please.
be doubt, but what happened that when we are calculating the mean with this kind of data, then again mean is getting influenced by this outlier. So I'm not getting how it's getting
Valid question.
compensated in that.
Valid question.
Yeah.
Valid question. So that's why we are discussing this technique,
Okay.
box
This
plot.
this one.
Therefore,
Okay.
you will not see mean somewhere. You will see the median. Right?
Okay.
Let
Got
me
it.
explain you this thing.
Yeah.
This graph is
Okay.
known as box plot. Box plot is a technique which is represented in a box form. It comes with whiskers. This is known as whiskers. This is the left whisker which goes toward here. This is the right whisker. This term is known as median. Median represents the 50th percent value. This is quantile 1. This is quantile 3. Quantile 1 is the value which is the 25th percent of the value. Quantile 3 is the value which is the 75th percentile of the value. After that, we have a whisker. Whisker is nothing but 70, and this range, Q3 minus Q2 ka range, this is known as interquantile range, IQR. And this value is known as quantile 3 plus 1.5 of IQR. This 99.9%, this is 1.5, but since I have not checked a long time, but still it is one. I will check it later. This is quantile 1 minus 1.5 IQR. So this technique says that anything which lies ahead of this Q3 plus 1.5 IQR, these are outliers. Any point which lies here, these are IQRs. So suppose in our data, these are the variables x2. So they are already method created in the machine learning suppose method name is box. I will pass the column name x2, and this box will create another column, say x2 box, which would be saying there, which would be basically giving you the outliers or box plot of that. And you can plot this xq here, and this will plot some, will give you a plot this. So now this is the technique which is independent of mean. So this answers your question, and a very good question. The question was that if already you are saying me that that x var plus 3 standard deviation, anything beyond that would be outlier. But my x bar is already, mean is already affected by the outliers. So will it be a right technique? So yeah, this is not a right technique, but one of the technique. But where we are strictly dealing with the outliers, this is the box technique.
Could you
Box.
maybe repeat one more time this box? I
Yeah.
missed that.
So let's create this box here. So, somewhere in the graph, you will see it in the vertical way. Somewhere you will see in the horizontal way. I'll keep it in the horizontal. This is known as box plot because this is just like other bar plots, etc. This is box plot. Uh, if I consider that we are moving from here to there, this is Q1, this is Q3. We are the center value is median. Median is the 50th percentile value over the data, sometimes also known as Q2. Q3 is the 75th percentile. What 75th percentile says? It says that 70% of the people has lesser value than this Q3. This is how we see in our percentile. Some examples we have already given. This is 25th percentile. The difference between Q3 minus Q1 is known as interquartile range, IQR. This is IQR. And this point, left side, this is Q1 minus IQR, 1.5 times of that. Q3 plus 1.5 times of IQR. Anything which lies beyond that would be outlier. Now this is come of why our research, whoever created the box plot, that what is the right number. But personally, this is the standard practice. But sometime I also I have kept it 2 for my use. So there is no mathematical justification that why I put 2. Maybe I want to be little more strict towards my outlier handling. That what was the nature of the data, so I made it 2, but actual range is 1.5 IQR. So this will make sure that you 99.9% you have already taken care of IQR. This is just based on median, so we have not taken mean in the practice. So this is mean agnostic, it's pure median dependent, and also pure depends on the percentile, which is nothing but the actual values where it lies. So any value lies here, these are outliers. This way also you can take care of outliers. So is it now make sense? So there are different
Yes.
techniques. You can see the mean based technique, and median based technique is the box plot, and there are many other techniques, but let's keep it these two. Check for multicollinearity I already discussed. We use the core function, and we decided okay, x1, x2, x3 are highly dependent on each other, highly correlated. If x1 increases, x2 and x3 are bound to increase. If x2 increases, x1 and x3 are bound to increase. In this scenario, the literature says drop any one. So maybe I drop the one which is least significant out of these three. I drop x3. This way we take care of future. Check for multicollinearity. These steps are checked. Then I will do the future scaling. I will normalize the data. I will see if there are some columns. I will normalize that. Then I'll do the categorical variable handling. If my sum data is A, B, C, I'll handle them. Right. Now this is some aspect. This is the steps which we must do if we apply linear regression. This makes sure that whether we are supposed to apply the linear regressions. To check for the linearity. So check for the homoscedasticity. Again, these all the steps are optional, guys. I mean 9, 10, 11 are very pretty much simple. So let exclude 6, 7, 8 for now. Future selection. Future selection says if I am given x1, x2, x100 futures, I'm not supposed to use all the 100 features. Maybe some are relevant, some are not relevant. The techniques of selecting the features, that is known as feature selection. And then what are the techniques through which you can select the features that, okay, X2 are important, X4 are X4 is the important one that we're gonna see later while doing the practical experiments. Split data into training and testing data. I already explained. In general, we split into 75 to 25% of the ratio. Why? That's the general case. We train on 75% of data and we test on 25. But for example, if my data is lesser, I might make it to 90-10. It just depends. This is not hard fix. I standard. This is just a standard practice, right? And then train and evaluate. We train the model. We train suppose model M1, M2, M3. Then we evaluate on test data. M1 gives 80% accuracy, for example, gives 85% accuracy, gives 90% of accuracy, or then I'll choose the M3. So these are the general steps. So when we will do it practical, we will be doing in this way only, right? Now, simply now let's end the day with just these 3 points, because otherwise it becomes very heavy.
Yeah. Here, this M1, M2, M3, these are like for different local minima. That's what the
Uh,
meaning. Yeah.
this is technically the way this is what it is. But in our case, model trained with some parameters, model trained with other parameters,
Okay.
with other initializations, with some different alphas. There could be many things. This trained with 64, this trained with 60-40, this trained with 75-25, 90-10, right? Later you will see this is a very basic way of doing that. But now after a few years, a lot of uh, very advanced ways already came up in which we train the models. So we will see that there are different techniques through which you can train the model in terms of data splitting. So yeah, coming for homoscedasticity, autocorrelation, linearity we'll see later. So what homoscedasticity says that if I'm training a model and what I see that for same feature over training different time, just a minute. I did some experiments. After full convergence, I got some values here. Then I did another experiment, or some after maybe some other iterations. I see the value somewhat here, and then I keep on doing the experiments. And for that column, for that feature or change in the feature, I see these are the values. So what I am seeing over the time, the difference is ranging of a huge. So ideally, what's with the nature that if I train some model, if I do different experiments, this value should be closer. And these value are nothing but the variance. If my variance is high over the time, it means my model is the data or that training is not perfectly done, or there are some instead of homoscedasticity, there is some heteroscedasticity. So this means that even if you do keep on doing this different experiments, there would be a huge variance. Huge variance means different y-hat value, and this is not we want. We do not want that every time we do experiment, we get different value for that row. Values would be different. I mean, of course, the value would be different, but it will not vary a lot. So if y-hat, suppose we train some model, we did some experiment one. I put row number one, which was the row one of test set. It gives me value 100. I did experiment two, same test key row two. I pass it, gives me value 200, 180. If I plot this thing, you will see that this is a huge variance, which is not right. I mean, there's some issue with the model training. What could be the right? 100, 105, maybe 100, 102. at max 110. So I see the values are almost percolating towards 105. But if I see that there's a huge variance for same row, after doing different experiments, I am getting value in a very big range. So this is nothing but the variance, a difference in the range. Variance is nothing but the kind of a range which is huge. So we do not want that. We want it to be closer to the actual mean of those selected values. So if I take that mean of these values, which is nothing but the y hat come mean, that should be very close to the actual values. But this is not the case. So this case should not be done. But now you would ask that how we practically handle these things during the experimentations. So practically speaking, and this you will not be directly doing it by yourself. So therefore I do not want to go into these two features because this is kind of a advanced way of handling the linear regression where you practically so just to summarize, and whoever understands, that's okay. So what we do, we calculate y hat for all the values. We calculate y hat, and then in y hat we reduce the y mean. And ideally, if we do that, these values is supposed to be like this. If I am seeing after even doing this aspect, my values are going high, it means there are variance. They are not normalized. They are, so this is pure noise. These values are random if you reduce the y mean from y hat. But even after reducing y mean from y hat, if my values are showing some patterns, so this is not acceptable. It means there are some variance. So little technical, but okay. Let's avoid 0.78. We never gonna do it by ourselves. For the scope of this course, this is more than even 99. Not for this scope, even for the practical example, the step 1 and step 5 are must. We cannot escape them, and 6, 7, 8 not required. 9, 10, 11 must. So these are the steps you will follow in your practical. We're gonna do each step here, excluding these three things. Just to mention, these are some important features which we generally check for. So yeah, so let me close it for the day. So therefore, already I mentioned here, following steps are applied in linear regression modeling in industry. Therefore, I do not mention these steps here. We do missing value treatment. We do outlier treatment. We do the correlation check of independent variables to remove the multicollinearity. Then we split it into train and test. Then we fit the model on train data. It means training on training. Fit is the word for training. And then we evaluate on the test data. And finally, if results are good, if I'm okay with 80% of the accuracy or whatever the metrics is here, I finally choose the model. These are the steps which suddenly happens in the industry. That is it. So, and any doubt in these 5 steps? I think this is straightforward, and these gonna be very cakewalk if after the first or second practical examples. It's pretty straightforward if we're gonna do that.
Raj, I have one doubt. I
Mhm.
think I may have missed it. Um, at the start of the lecture, we were looking at the local minima, right?
Mhm. Yeah.
And in which step did we found the global minima? By changing the theta 0 and theta 1, there we found the global minima, right?
So no. So were you there when I mentioned that why change gradient descent, this algorithm
Yeah.
will make sure that you end up in or reaches near a minima that would be a local minima. It will never be a global
Yes.
minima.
Yes.
But then I mentioned this gradient descent algorithm is known as vanilla gradient descent algorithm. There are techniques such as SGD, ADAM, ADAGRADE,
All
all
right.
do
You mentioned the
right.
item. Yeah. Yeah. Now I
These are
recall. Yeah. Sorry.
yeah,
Yeah.
these are the advanced techniques which will later will try. Of course, this will work, not sure, but this will try to reach you to the global minimas. But
Yeah. Yeah. Sorry.
experiment, no
Yeah.
issue. Experiment says that even if you achieve a local minima here, this is quite good, right?
Yeah. Yeah. Understood.
Yeah. So now these days, when some algorithm we just call these days algorithms are already there. We just take make an object of that and These are already created as a class. We make object of that, pass the data, do the model training. In itself, they are
Yeah.
so well written that they already use Adam by itself or whatever the best. But they give us the option. If you that my our default is Adam, do you want to go with the other grade? So we can provide that. I'll show you. So okay, for
Yeah.
example, yeah, okay. So time is not there. So okay, let's come up to the end. I've skipped one thing here, and so this is a way of evaluating. I'll do it later. Later means I will not skip it before next algorithm. I will finish it, and then yeah. So lastly, there are lots and lots of improvement techniques or the data selection technique, but I would like to mention couple of just two techniques here. Again, not the scope, not the scope of the exam or something, but it's better. So I will introduce two terms here: overfitting. I already So when I mentioned that we evaluate and train, we this is train test. It always plateaued. At some point, it start going up. Now, overfitting is a technique. Says that you keep training your model for such a long time that over the time is start seeing samples repeatedly, and instead of learning the patterns, it start memorizing. That's called as overfitting. That model is so well. So practical example, very good example here. This is my data points. Same data points. Same data points. Trade-off or optimal. Overfitted. I'll show you. Underfitted. Fitted means if just for the mind mapping. Undertrained. Overtrained. Just repeat as fitted. Fitted. Overfitting says that my model is somewhat this way. It is supposed to be a linear regression line, but it is so trained, so superly trained that it always memorize all the points. So this is called as overfitting. So this works well on this data, but some generalized data, it fails. This is kind of overfitting. Your model has basically memorized all the points values. Optimal line maybe somewhat here. Underfitted. Even your training is not completely done. You are undertrained. So this is we do not want this case. We do not want this case. We want this case. So that's what we want to do it here. So this is known as a trade-off between underfitted and overfitted. Technically or in MCQs, this term underwise, this is known as biased. This is known as variance model. High variance, high biased, highly biased towards highly biased toward these points. So they are not even trained. They are just underfitted. They didn't consider the effect of these data points. So the, there could be many regions we do not train for long. We keep the number of features not sufficient enough to learn the patterns. There could be any number of ways. Here we trained so much long, and we have considered so much data, seen data here, that it almost fitted all the points which we do not want. So these we always want a trade-off, and trade-off lies somewhat here. So that's the very good part of linear regression. All the trade-offs, everything boils down to this thing. We always target the minimas here, right? So linear regression is a simple and powerful technique, but it has some limitations, specifically when dealing with the multicollinearity. There could be x1, x2, 100 columns which are so much linked with each other, and the data could be overfitted. So after then, there was some scientist. He has created a two algorithm, Lasso and Ridge. Lasso says that in summary, Lasso says that considering this x5, Lasso algorithm does that if x5 is not relevant, is not a good future. Again, this is part of future selection. If Lasso says that if this is not a good feature, I will penalize it by making its coefficient 0. So basically permanently removing this feature from here. This is what Lasso did. What risk regression does, it says that considering the x5 only, if I am not a good future, you add me here, but I am not a good future, then I will not permanently remove it, but I will make its coefficient very close to 0. So basically restricting down is effect to negligible. So this is what lasso and risk does. So these are the two techniques which basically penalize your future if it is not, if it not at all or very rarely helping the model by model, right? This is what lasso and restriction shows that technically, and if and and how it works, very simple. Let me say if I remember alpha delta j by delta theta 1 theta, this is theta 1 theta 1 theta 1 minus plus one more term is added here, lambda. Here this is for lasso this is y minus y hat for training data ka absolute. So if you are very far away from me, I mean if my predicted value is very far away from me, I will penalize you more. Theta will be reduced a lot. So we added one term here. So this absolute term lambda absolute y minus y hat, this term will be added here to penalize. This is a penalty term. In lasso, this is absolute. In risk, this is squared term, right? So basically we added one term. If difference is huge, it will make theta changes a lot. Absolute will make sure that theta reaches to 0. So just for the understanding, this is the uh, linear regression ka uh, better version known as lasso regression and ridge regression. So only thing which I would be helpful for us to remember under the scope of this course is that there exists some techniques which basically penalize the columns if that columns are not helpful in the model training. Therefore, if I use lasso, it will automatically reduce the columns which are not which are not good columns, and basically by doing so you are already doing the future selection, keeping only the relevant columns. That is it. So this is what we need to know from this regulation techniques. And again, this is one liner when you do it practically. So just to understand, I'll reiterate it. In linear regression, we aim to find the best fitting line, minimizing the sum of squared error cost function. Suppose we keep on adding more and more features. Just be with me. We keep on adding more and more features that it may cause following issues. First issue, you may have added many correlated variables which eventually make your coefficients high. I already see that. You might see the problem of overfitting when adding so much columns that it started learning the data. So why not add some penalty to the cost function such that if the added variable is not helping in the optimal model, it would be penalized. By penalized means it thetas will either becomes 0 or in this regression theta becomes tends to 0. That's what here. That's the mathematical depiction which we do not gonna go right now. Okay, so that is it. Comparison between ridge and lasso reduces multicollinearity by shrinking the correlated feature coefficient, means tending it to 0. Shrink some feature to 0 makes theta equals to 0. So straight away reduce the columns. This helps feature selection, or this helps controlling the larger coefficients. For example, if some thetas are way higher, and this means this column is not good, then this theta will tend to 0. So prevents overfitting. Here, all the features would be there. If I have 100 features, I will keep all the 100 features. However, some of the features coefficient would be 0, which means practically giving very least effect to the y hat ka prediction. Here we make most of the columns to 0, right? This is the difference. And now somebody says that, again, some researcher came, he said that why not keep both together? So they make another algorithm which is known as elastic net regression, which is nothing, which is same. Now our J function would be theta 1 would be theta 1 minus uh, alpha delta of delta theta 1. J function becomes that's that cost function plus lasso ka penalty function, which is lambda 1 y minus y hat, lambda 2, which is y minus y hat ka square. So दोनों को add कर लिया, they added both. This becomes your elastic net. So this, they keep on doing different experiments. So if I also want to make sure that that both the penalties are added, also whoever knows, this is known as L1 penalty, absolute penalty, this is squared penalties, L2 penalties. But okay, that is what it is. And believe me, we have all, if you even go for, these are the things which I've referred while created the slides. The basic stuff diagram which you have seen, that has been taken from machine learning and UNG. Wikipedia I use a lot, and CS29 video 2029 videos, I have taken some good examples from there. So we have almost studied linear regression theoretically in the manner that we have covered most of the stuff which helps us in the industry level. And yeah, this is just all about practice. So time is not there, but before starting the next algorithm, I already have one problem with us, which I was supposed to do it right now. So the next class we gonna see a use case, which is basically this. We wanna work on e-commerce company data set which sells clothing online. They also have in-stores clothing advice sessions. Customers come to the store, have session meeting with personal stylists, kind of a startup. So they want to focus. They company is trying to decide whether to focus their effort on the mobile app experience or website. They want to see whether the customer purchases more from the mobile app or website. They have hired some contracts to help them figure out. So what they have done, they have provided us the data. They have provided us data in the form that they have provided us average session of in-store style advice sessions, average time spent on the app, average time spent on the website, how many customers has been a member, and so on and so forth. Based on that, we want to come up with a problem case here, right? This is we're gonna work that. The data looks like that: email address, their avatar, their average session, time on app, time on website, length of membership, yearly amount spent. This is my Y column. So basically, I want to see who spent more. First thing first, this is a supervised algorithm. We have the data, we have the data, and we have the label. This is a continuous problem, continuous data, yearly amount is spent. Therefore, we can think of applying linear regression. And this is how our data looks like. Like every row, we will we will we will read it in a CSV, then we will do the experiment, right? So this is how we're gonna start working on that, and then you will see how we work on machine learning. So we will download some libraries, we will read the data, we will evaluate that, we will do some exploratory data analysis, how the data looks like, you will understand, and then we will plot some graph, then we will see how the data looks like, and then we will train the data. We will split it into train and test. We will train the model, we will predict the test data set, then we will see how the predictions look like, and so on and so forth. And then we evaluate the model, how the model works, right? And this way we will conclude what is our finding, right? This one we're gonna see in next class. And after that, we're gonna work on our second algorithm, which is known as logistic regression. So my second algorithm would be logistic regression. Logistic regression is an algorithm which helps you classify between two things. So for example, whether you are a defaulter or you are a non-defaulter. That's a classification. When you classify your data in some classes, you are doing a classification, and logistic regression is one of them. So yeah, we are already over the time, guys. So let's keep it this way, and please refer before we start this thing. At least refer the today's session before coming to the next session. Would be helpful for us, so, seeing all the points again practically in practical terms. So this slide is already shared with you, so you can just have a look once again. Is anything to be discussed quickly before binding up? And hope
No,
50
not
60% things make sense. I'm that's sufficient. And
Yes.
yeah,
some of them do, but as I said,
yeah,
uh,
I
we need
understand.
to revisit and then because there is a lot to grasp.
Yeah, that's yeah. So yeah, please keep revisiting it. So based on my learning from the past batch, I took a lot of algorithm, because
Mhm.
but right now I will take a very small set of algorithms, 4 or 5 maybe, but from
Okay,
different areas.
okay,
But for that you would be able to have a good amount of time, right?
okay.
So
Yeah,
but yeah, so please do visit the slides once.
definitely.
Thank,
Yeah,
yeah, thank you everyone. See you then. Good night.
thank you.
Bye.
Yeah,
Yeah.
bye.
Right.